Hello everyone, myself A.Yadagiri, Assistant Professor, Department of EEE, MLR Institute of Technology, Hyderabad. I'm also the Faculty of Basic Electrical Engineering. So in the last session, we have discussed about the problem based on the RL, then RC, and also the RLC series circuit. So in this session, we are going to discuss about the resonance condition in RLC series circuits. So before going to briefing about the session, so now the overview of the session. So need to discuss about the resonance condition in RL series circuit, and based on that, how we are able to get the RMS value of voltage for the whole circuit, and also the how much amount of current circulating under the resonance condition. So based on that, how much amount of the impedance suffered by the RL series circuit under resonance condition, and after that we need to discuss about the phase angle of the circuit under resonance condition, and also the power factor, and as well as the real power of the, the whole total power supplied to the circuit also we need to discuss. So before going to discuss the resonance condition in RL series circuit, first of all, what does it mean by the resonance condition? The resonance condition of the any system occurred in anywhere or any system, we require two energies. So two energies are going to present at a particular instant of the any system or any the network or anything. That's called simply resonance condition. Means whenever we need to get the resonance condition, we require two energies. So for that reason, we will get the resonance condition as well in the circuit or any system. So similar to that, the resonance condition occurred in case of the RLC series circuit. So also we require two energies. So in case of the RLC series circuit, so the energy came from the inductor in terms of the magnetic field, and the energy so given by the capacitor in terms of the electrostatic field. So here we also require from this network two energies to get the resonance condition. So based on that, inductor and also the capacitor should supply the energies to the whole network. So based on that, we will get the resonance condition. How we will get the resonance condition in RL circuit means, so if the two energies are present over a particular instant, so with the wide variation, that corresponding instant of the circuit is said to be resonance condition. So that means, so the occurrence of the resonance condition in RLC series circuit, so the energies are, the energy in the inductor and also the capacitor are going to present at a particular instant with the wide variations. That corresponding instant of the circuit is said to be resonance condition. So at that instant, the energy exchange is going to happen. So due to that reason, so the energies are going to equal together. So based on that one, the energies are going to cancel together in the inductor and also the capacitor. So in terms of the magnitude wise, both are equal, but in terms of the direction should be opposite. Based on that, so these energies are going to get cancelled. That corresponding instant of the RLC series circuit is said to be resonance condition. So also we can say in terms of the reactance of the network. So whenever we need to get the net reactance of the circuit should become 0. So then the electrical resonance condition is going to occur in case of the RLC series circuit. To say the RLC series circuit is said to be resonance condition or resonance instant. So the net reactance of the RL series circuit should become 0. So that corresponding instant also we can say to be resonance condition of the RLC series circuit. So for this case, let us take the RLC elements are considered in series. So here the R of the network is said to be resistance of the network. R is said to be resistance. So resistance of the circuit, and we can say here the inductance offers some kind of ohmic property that's called XL. XL equal to, we want to say it's a 2 pi FL. So it was already discussed in the earlier topic, that is in case of the RLC circuit. So in that we will get the XL value. So the XL is nothing but it's a reactance of the inductive coil, that is a 2 pi FL. It is a reactance of the inductor or inductive coil. The next one is, so the capacitor also offers some kind of ohmic parameter, ohmic property, that's called XC. XC means it's a 1 by 2 pi FC. XC is a 1 by 2 pi FC. So which means it is a reactance of the capacitor. It is a reactance of the capacitor. It is a reactance of the capacitor. R means the resistance of the circuit, and XL means the reactance of the inductor, and XC is the reactance of the capacitor. So under the resonance condition, the circuit is said to be, RLC series circuit is said to be resonance condition. The net reactance should become 0. So at that resonance condition, we need to find out the total impedance of the network. So the impedance offered by the whole network Z equal to, that is say the total impedance. So in the whole resonance condition, we need to analyze the how much impedance offered by the whole network, and also based on that how much amount of current circulating to the whole network, and based on that how much amount of the power factor offered by the whole network, and based on the resonance condition, then how much amount of the total power absorbed by this network. So these many parameters we look into. We need to derive in the whole network. Under resonance condition, we need to find the how much impedance offered by the network, and also how much current flows through the network, and based on that how much amount of power absorbed, and based on that how much amount of the power factor offered by the whole network. So for that reason, need to find the first and foremost parameter, the total impedance. The total impedance under the resonance condition. So the total impedance at any frequency, first of all, at any frequency. So that is, we can say Z equal to R plus J times of XL minus XC. So the magnitude of Z value should be, it is a square root of R square plus it is a XL minus XC whole square. So this is the total impedance of the network for any instant. So we need to substitute the XL and XC values. So in the in the beginning we have seen that XL and XC values. So these are going to substitute in this expression. So we will get the impedance of the network. So that is, so Z equal to again square root of R square plus it is a 2 pi FL minus 1 by 2 pi FC whole square we got, minus 2 pi FC whole square we got. So the resonance occur, the resonance condition occur in RLC series circuit. The resonance occur in RLC series circuit, that is XL equal to XC, which means the net reactance of the circuit is 0. That's called XL equal to XC. So under this instant, the impedance of the network, both are going to get cancelled together. So then the whole impedance offered by the network should be equal to, it's a square root of R square only. Both are gets cancelled, means the total impedance under the resonance condition, that is a Z equal to, ZR equal to, it is a R only. So the resonance, the impedance offered by the network under the resonance condition is said to be dynamic impedance. This is called dynamic impedance of the network. So it is a dynamic impedance. The impedance offered by the network under the resonance condition is said to be dynamic impedance. So that's we can represent it by the ZR. So it used to run the maximum amount of current. The dynamic impedance of the network should be accepting or should be caused to run the maximum amount of current. So at this instant, so we need to find the current value. So this one is a dynamic impedance, we can say. So under the resonance condition, the impedance offered by the network should be equal to ZR equal to R only. So at this instant, the whole network should should accept the maximum amount of current. So that we need to find the that current should be maximum. We said that the current value should be maximum. So that we need to find, that is a IR equal to, current under the resonance. So current under the resonance condition. So current under the resonance condition, that is IR equal to, it is a V by, it is a ZR. So that is a IR equal to V by R. So this much amount of current taken by the network under the resonance condition. This one we have already seen in case of the pure resistive case. So whatever the current taken by the pure resistive network or pure resistive circuit, the same only, the same amount of current only we got here. So under that condition, the phase angle between the voltage and current of the network should become 0. Why? Because the voltage and currents are both are in phase. So this is the voltage we can say, and this one is the current. So both are in phase. Whatever the current circulating under the resonance condition of the RL series circuit, which is same as or similar to the pure resistive network. So based on that, the phasor diagram or the phasor representation between the voltage and currents are in phase. So based on that, the phase angle, that is a phase angle, that is a pi r should become 0. Hence the power factor, that is a power factor of the system or power factor of the circuit under the resonance condition. So that is a cos pi r equal to, that is 1. Under the resonance condition, the power factor should become unity. So based on that, it would like to take the So huge amount of maximum amount or maximum amount of the power. So we need to find the ZR value and impedance offered by the network and current flows of the network and also the power factor and based on the phase angle. So these many things till now we have done, and after that we would like to find the current the power value, power and the power factor value. So power factor we have already derived, that is one only we got. So we also look into the power factor one more, in other way. So cos pi r equal to power factor under resonance condition, we can represent it by the cos pi r, that is the ratio of the resistance to impedance. So impedance also we need to keep like r means under resonance condition only. So based on this one, r by r we will get again 1 only. Hence the power factor under the resonance condition should be equal to unity, that is 1 only. So this is again one more method to deriving or to finding out the power factor of the circuit under the resonance condition. So if the power factor maximum means, so we got here the power factor should be maximum, means the power absorbed by the whole circuit will be maximum. If the power factor should be maximum means the power taken by the whole circuit should also be maximum value. So based on that one, we need to find the power under the resonance condition. The power under the resonance condition. The power value under the resonance condition. So what we can say means, it is a power under the resonance condition should be equal to, it is a V into I cos pi. So this is the active power taken by the, or useful power taken by the circuit. Under resonance condition means, this means IR and this means pi r. So based on this one, need to substitute these all values. Then PR equal to V as it is, then IR should be equal to, so V by R according to the Ohm's law, because we have derived the current value under resonance condition. This one we need to substitute. So for that we will get this as the PR equal to V into V by R. Then cos pi R value should be, this is R by Z. I mean to say R by R only. RR gets cancelled. Then the power under resonance condition should be V square by R. So this whole term will become 1 means. So then the power taken under the resonance condition of circuit should be PR equal to V square upon R. So V square upon R. So the power should be maximum under the resonance condition of the RLC series circuits. So next we would like to take the one more parameter. So that is under the resonance condition. Under the resonance condition, the net reactance will be, that is XL minus XC equal to 0, which means XL equal to XC. What we want to finding means, we need to find the voltage across the each element under resonance condition. So we need to multiply the IR into the both side. I mean to say IR into XL, then IR into XC. It is according to the Ohm's law. This one we set to be VL equal to VC. So VL minus VC or VL equal to VC. VL minus VC equal to 0 means VL equal to VC. So this much amount of voltage taken by the each element, to say voltage taken by the inductor and capacitor under the resonance condition. So we want to say finally, so under the resonance condition, the voltage across the inductor is equal. Equal in magnitude and also the opposite in direction. So based on that one, so the voltage across the inductance is equal in magnitude and also the opposite to in phase. So therefore the net voltage of the network, therefore the overall voltage. Next we need to find the net voltage of the network. The net voltage of the circuit under the resonance condition. The net voltage of the circuit under the resonance condition. So means it is a V equal to the square root of the magnitude value. We need to consider square root of VR square VL minus VC whole square. I mean to say, So under the resonance condition, the voltage across the inductance is equal in magnitude and opposite in phase. So based on that one, so the voltage across the inductor should be equal to the voltage across the capacitor. So the net voltage should become, so that is V equal to square root of VR squared. Finally V equal to then I into R we got. I mean both are gets cancelled. We'll get the V equal to VR only. I mean to say VR means voltage across the resistor only. So under the resonance condition, the net voltage will be equal to the voltage across the resistor only. So whatever the voltage appear across the resistor, that is the net voltage of the network. So that we can expand in terms of the Ohm's law means it is I into R. So based on this one, we can say, so under the resonance condition, the whole circuit draws a maximum amount of currents. Hence it is called, so it is the acceptor circuit. I mean under the series, under the resonance condition of the RLC series circuit, going to take or draw the maximum amount of currents. Hence it is called as the acceptor circuit. It is the acceptor circuit. It is acceptor circuit. So under the resonance condition, the whole circuit should take the maximum amount of current and also the maximum amount of power. So based on this reason, the whole network under the resonance condition is called as the acceptor circuit. So the summary of the session, till now we have discussed about the resonance condition of the RLC series circuit. So in RLC series circuit, I mean to say the RLC series circuit should be an electrical resonance when the net reactance should be equal to 0. I mean XL minus XC equal to 0. So then the frequency at which the resonance condition is set to be the resonant frequency. So this one we have find. Then after that we also find the network impedance value. I mean under resonance condition, the network impedance should be equal to the R only. So based on this, I mean the impedance suffered by the network or RLC series circuit, that is Z equal to R means, so we can call it as the dynamic impedance. I mean to say the impedance under the resonance condition is said to be dynamic impedance. That value should be, so ZR equal to R only. So based on this one, we also determine or we also find the current value. So under the resonance condition, the current should going or should enter into the whole circuit should be maximum. So that is IR equal to V by Z means V by ZR means V by R only we got. So based on this one, it used to take or draw the huge amount of or maximum amount of current to the network. So then after that, we have also find the power factor angle, that is a pi R equal to 0 we got, and also the cos pi R equal to unity we got. So based on this one, it used to take the maximum amount of power, that is a V squared by R. So whatever the active power consumption taken place in case of the pure resistance, so same amount of the maximum power taken by the RLC series circuit under the resonance condition. So based on the these two condition and this one and also this one, so the whole network is said to be acceptor network. I mean to say, so under the resonance condition, the RLC series circuit should take the maximum current and also the maximum power absorption. So based on this one, the corresponding network is said to be acceptor circuit. Acceptor circuit. So this is the acceptor circuit. So this is the end of the session, and in the next session we are going to discuss about the what do you mean by resonance frequency and also the quality factor offered by the network under resonance condition, and after that what do you mean by bandwidth of the network. So these many things we need to discuss in the next session. So thank you one and all for this session, and thanks for watching.